Okay, good afternoon, everybody. My name is Boelo Schuur. I am the Scientific Vice President of the EFCE, and I have been in the board since January of this year, and I'm a chemical engineer by training. I received my education at the University of Groningen in the Netherlands, and after staying a while at the Technical University of Eindhoven and in MIT, I joined the University of Twente in 2011, and currently I'm a full professor in separation technology. And I'm very happy to be involved in the introduction of this webinar on safety challenges in the era of energy and digital transition. And I'm looking forward to participating in it. Let me say something about the Spotlight Talks. This is our 5th year of Spotlight Talk initiative, which started in 2020 in the COVID pandemic. During the past years, we have seen this is a successful means of communicating with the chemical engineering society. And that is why we have transformed it into a recurring event in the even years like this year. We have a spring session and a fall session, and in the odd years where we have the European Conference on Chemical Engineering, we only have a spring series. This fall, 13 of our working parties and sections, sustainability, mixing, electrochemical engineering, high-pressure technology, food, loss prevention and safety promotion in the process industries, agglomeration, multi-phase fluid flow, static electricity in industry, education, polymer reaction engineering, thermodynamics, and transport properties, and early career chemical engineers are delivering in a period of 2 weeks' time short sessions of 3 or 4 talks focused on specific topics by leading industrial and academic experts. The series also enables attendees to sample matters in new areas, encouraging the cross-fertilization of interests. The complete program is available on our EFCE website. And the EFCE promotes a scientific collaboration and supports the work of more than 100,000 chemical engineers throughout 30 countries in Europe. The EFCE working parties and sections cover all major specific aspects of chemical engineering and are the core of our organization, forming the scientific engine that drives the EFCE activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. And I'm particularly happy that in this series of Spotlight Talks, we will have the this contribution of the working party on loss prevention. I would like to thank all the working parties and sections in this whole series, but specifically today, Bruno Fabiano as the chair of the working party on loss prevention, and of course, Martina Poo for organizing this series. I would like to pass the word to Bruno Fabiano.
Good morning to all. I hope that Martina will share the presentation now, because I had, yes, good. So I welcome the participant here to the Spotlight session organized with the involvement of the Loss Prevention Working Party within the 7th EFCE Spotlight Talk series, which, as already stated, covers up-to-date chemical engineering topics. A few words just. My name is Bruno Fabiano from University of Genova, Department of Civil, Chemical and Environmental Engineer, and I'm currently the chairman of the Loss Prevention Working Party of the European Federation of Chemical Engineering. Just let me express my thankfulness to Martin Poo and her co-workers for making it possible to have this low barrier opportunity to get involved into the activities of our working party. Even though my task here is the simple presentation of the speakers, I see that we have a large number of participants, both young and experienced, so please allow me just to spend a few words about the Loss Prevention Working Party. This was founded in 1971 and covers all aspects of loss prevention and safety promotion with people from academia, industry, regulator bodies from outside Europe, with currently 29 delegates. More than 50 years of loss prevention and safety promotion can be seen and are outlined by the history of our symposium. And here you can appreciate the different hosting countries from the origin to nowadays, and the next one, which is planned in Bologna. In the next slide, you can see the development of loss prevention aspects over a time span of more than 50 years. And it was expressed in this crown format for safety management in 1995 at the 8th Symposium in Antwerp by Koos Visser from Shell. And since then, it was stepwise expanded by Hans Passmann. You see that the attention shifted from explaining after the fact the accident had occurred via designing and implementing protective measures towards prevention by inherent safety features and rethinking the process. And nowadays, we added as an overall umbrella resilience building, which is under full development to support business continuity. So the Loss Prevention Working Party organizes every 3 years the Loss Prevention Symposium and aims at disseminating process safety good practice, discovering new techniques and approaches, gaining experience and lessons from past incidents and near misses, allowing as well international networking among academics, industrial experts, and consultants. I invite you in the next slide, you can see that in the loss prevention website, you can find under the section history, the content and full papers of all symposia, actually representing the history of safety and loss prevention with free download. And you can find the link in the EFCE website. So we can say that the safety community succeeded in getting better control over the risk of operation. And nowadays, the symposium, more than ever, aims at being broad in its scope, bringing all process safety aspects together to raise and expand the culture of safety. On this ground, the following symposium, the 18th, will be organized in Italy and in Bologna. You can see the following 2 slides. This is the leaflet of the Loss Prevention Symposium, and the next one shows that Bologna is the oldest university site in Europe. In this symposium, we introduce new topics, which takes into account the newer needs of industries and the EFCE efforts to transmit the key messages relevant to energy transition, carbon-free, and safe and sustainable industry. In the next slide, you can get an idea of what are the current topics, and you see that safety 4.0, AI, digital transformation, sustainability and resilience in the process industry, new materials and technology, safety and security of chemical and energy infrastructures are really up-to-date topics. Additionally, as you will notice, in the next slide, in light of the recent issues posed by energy transition, digitalization, and required risk consideration and assessment methods, there are a number of specialized sessions which are planned and are chaired by leading experts. And you can see, for example, cybersecurity in the digital area, safety of liquid hydrogen, integration of process system engineering with machine learning, and so on. And also on these grounds, this webinar is organized to provide a flavor of the symposium, and it covers in its program both technical and human organizational aspects of the expanding loss prevention and process safety horizon. So the next slide shows that we have 5 contributions, and I hope that you can sample novel ideas and encourage cross-fertilization between specialist areas. Just let me spend a few words about the speakers. The first one, which is in the next slide, is Alexis, who is PhD in chemical engineering, and he is an expert in process safety in chemical, pharmaceutical, and food industry. He has worked for over 19 years as consultant in the field related to risk assessment topics as major accident, ATEX, electrostatics, thermal process safety, and facility design. He currently is a global HSE manager at STAHL. The next speaker is Mondie, Mutegi, who holds a PhD degree in mechanical and process engineering and has over 10 years in professional experience in the field of process and plant safety, especially in the areas of pressure relief and thermal process safety. The next one is Alessandro Tugnoli, professor of chemical engineering at the University of Bologna. He has he is principal investigator of the Horizon Europe, Alexis and Nicola projects addressing the safety of novel concepts for large-scale liquid hydrogen exploitation. The fourth speaker is Rustam Abubakirov. He is a young speaker, and he is currently PhD researcher in the Safety and Security Science section at Delft University of Technology, the Netherlands. He has main research topics focusing on machine learning application for process safety and risk assessment and safety management of ammonia-fuelled ships. At last, we conclude our spotlight talk with Professor Nicola Paltrinieri, who is Professor of Risk Assessment at the Department of Mechanical and Industrial Engineering at the NTNU in Norway. And he is also adjunct professor at the University of Bologna. He serves as Norwegian delegate of the EFCE Working Party of Loss Prevention and Safety Promotion. Now it's time to get the spotlight talk off the ground, as the full program is dense of significant topics and we have a tight scheduling. And I'm not going to lose any more time, and I'd like to wish all you a very interesting and inspiring afternoon. I remember that we shall have a concluding question and answer session, so please at the end you can write your question and the speakers will hopefully open the discussion. I suggest you to be unmuted during the presentation. I'm giving immediately the floor to the first speaker, so please, Alexis, the floor is yours.
Thank you, Bruno. I will share my screen.
Good.
Do you see it?
Yes.
Okay, very well. So my presentation, I will speed up a bit and try to finish as close as possible to the original time. The concepts are simple. It's about safety culture and how you can challenge emotional or biases with data. So let me start with this. That was kind of the perception that we had. And this is a famous sentence from Donald Rumsfeld, who said that there are things we know that we know, others that we know we don't know, but also there are things that we don't know. So when you apply that in practical terms in chemical industry, we face a situation like this. So the operators or the first line daily operations need to perform actions. And many times these actions are defined in terms of safety concepts from an health and safety desktop, so somewhere remote to the plant. And the knowledge is not perfect. So typically there are a brighter number of questions to be solved than the ones which are known at, let's say, safety or corporate safety departments. But in those departments, many times you have also a lot of more knowledge than the one that you end up putting in the protocols, instructions, trainings, etc. So as there is no perfect match, the question or the situation is that sometimes operators need to solve question with lack of know-how. And at the same time, there is relevant know-how left out of production instructions. So it is essential to understand the needs. And that is something that we identified at STAHL. So I will not go into detail. I just want to show you how was the old reporting system. So you see there are several blocks and several tools, like some local reporting system, then Excel, SharePoints, Words, etc. And what we saw clearly is that we had data lost at the early steps. In a reporting system, it's very important to be effective. Otherwise, if you don't remain effective, it's very difficult to manage big amounts of data. And that we kept in mind. To generate statistics, to generate data, you need to be very effective. So what we did is implement an integral tool covering all steps. So we wanted with a new tool to have all data collection, all data analysis, and drawing out conclusions from the same platform. I will go a bit into the details, and then I will show you the results that we obtained when we implemented this tool. So at STAHL, we define three types of reports: damage, close call, or near misses, and observations. They are familiar in the safety world, so we'll not explain the difference between them. Just to mention that for us, a close call, or in terms of LOC, loss of containment, is anything below 1 kilogram, and anything above 1 kilogram is a damage. And on top of that, we apply the CEFIC criteria on process safety indicators. So that does not mean that everything that above 1 kilogram is per se a relevant process safety event, but we report it as a damage. And an observation is just an observation, nothing happened. So the first point, and the thing that I mentioned before, is we wanted a system that could be easily accessed. And this system has three ways of reporting. There is a module, which is web-based, where you can log in with your user, but this is typically for managers. The most frequent way of reporting is a reporting portal or a reporting app, which is available for smartphones, tablets, etc., both in Android and iOS. So we wanted to bring the barriers for reporting as low as possible, make it really easy, accessible, and fast. The workflow was also important, because if you define a very complex workflow, then it takes a lot of time between something is reported and closed, and we wanted to keep it short. So I will show essentially the ideas or what has to be done at every step. In first place, you have a first report, and you just the people reporting just need to put a title, a description of what happened, and the actions taken. If they want, they can upload pictures, and all this info is in local language. We have plants in China, India, Brazil, Mexico, US, Netherlands, so worldwide. And to lower the reporting barriers, you need to allow them to report in local language. So when the first report is submitted, it's a draft. And then if this report is valid, we have to translate things into English, assign an ownership, and define the type of consequence. And then when it sets in progress, depending on the type of report, there are things to do. If it's an observations, you can directly define actions to correct this observation and prevent it from happening in the future. If it's a close call, the option is there to issue an investigation and also define actions. And in case of damage, consequence assessment, investigations, and actions are mandatory. After that, the event is reviewed, approved, and closed. So the key point here, when we focus to be very effective, is to keep in mind that we need to simplify the understanding of what's happening. So basically, we want to have clearly what is the intended condition, what was the deviation, the cause for the deviation, consequence, safety measures, if they worked or failed to work, and the actions that we will take to avoid again this or to ensure that the intended condition will not deviate in the future. We developed these concepts. I will not go into the detail of the methodologies, but we developed that together with the operational excellence and global quality managers, because we wanted to standardize also practices between departments. So when there is a quality issue, operational excellence issue, or a safety issue, we all use the same tools. In terms of implementation, first you see here the type of consequences that we may have. and you can select this is a screenshot of a part of the event reporting. Then we also identify what factors are relevant, like behavior, equipment or facility condition, instructions or protocols, external factors, and natural hazards. And we all do this with some selection list. So you click and there are several levels, but it's not free text, because in case of free text, the data assessment, it becomes very different, because some people use different words worldwide to refer to the same thing. So the position was, we need to standardize, so we use click lists. We also define the operational conditions and the relevant assets. What has been the effect of implementing this system? Well, you see the frequency rate in terms of reporting of observations and close calls. And the frequency rate is the number of events reported divided by the number of hours worked and times 1 million. So you see that the increase since we implemented the system is really huge. So, but this is not the end. Then we also develop some infographics with using Power BI, the Office platform from Microsoft, to make it visual what's going on. And this is what all plant managers, safety managers, so everyone at STAHL has access to this info. So they can select what's going on in their plant and then understand what has to be done. So I will show you a few of them. So the first thing that we can see and we can ask, are we reporting enough? Well, in this figure, you see that we are reporting a lot more observations than close calls and more close calls than damage, which is in terms of the bird permit, it's okay. And that was not the case before we implemented this system. Also, we can see where is our awareness. If you remember the definitions, a damage or close call, near miss, is where something actually happened. The difference is the level of severity. So we see that in terms of damage of close calls, things actually happening, we have more LOCs than injuries and more injuries than asset damage. While if we look at the observations, we see that the most observations refer to people potentially getting injured. So we identify that people has more awareness to situations that can cause an injury than situations that can cause an LOC. But in reality, we have more LOCs than injuries. So that was interesting to understand why, for instance, we have this LOC level. We can also assess the safety pillars. And you see here the safety pillars. So typically you tend to see that many times it's just said, most of things that happen are just behavior. Well, in this case, we see that behavior is a very important part, but equipment condition is identified many times also as a critical safety pillar. And if we go a bit into details of this, the concept that we are applying is, if we compare behavior and assets, equipment condition, we are implementing this concept. If behavior and assets are wrong, then this is really a threat to kill the activity. If you only focus on behavior, but you are not improving the assets, at the end people is really fed up because they want to work in a safe way and they are just fighting with equipment that is not working. And we saw that also in other safety forums with other companies. If you invest a lot in assets, but the behavior is still bad, basically you are not making good use of money. You are burning money because the assets which are brand new with a bad behavior will degrade or become very easily in a bad condition. So the only sustainable and good corner is where you have good assets and good behavior. And being fair is important because if we focus only on behavior, well, we know that we work with people. People is a lot less reliable than any automatic control system. So we need to be aware of that. We need to keep fairness, but also make people understand that safety starts also with behavior. So there is a clear relation. Now, if we focus on behavior in sites, what we learned is that a significant number of behavior issues, and this is not just damage, it's damage, close calls, and observations, are neglected instructions or protocol. Why people are neglecting instructions and protocols? Well, time pressure, lack of perception that what they are doing is important to be done in a specific way. And we are addressing that with leadership and discipline. Be clear and be fair. Because we need to understand that there's a difference. For instance, if you have a checklist with a signature or a confirmation in a control panel and you neglect to do it, typically is a neglected instruction. But if you have just a generic instruction requiring a check, for instance, before starting a transfer, check that the facility is in the right condition. Well, it is requiring a check, but it's not specific, and we can make a mistake. In this case, we classify that as an attention. The root cause in terms of behavior is not enough attention to process setup. But of course, you can make once a mistake, but twice or thrice. So at the end, we can also assess that as a neglected instruction if we see that this is happening several times with the same person. But we want to remain fair. This is really important. We also could identify that sometimes lack of automation is playing a role. So that is helping us to identify what parts should be better automated. And we keep it simple. We are thinking typically of a position switch and an interlock, avoiding LOCs, for instance. Movement awareness, slips, trips, and falls, the line of fire concept, etc., is also an important part of behavior. And again, if we fail to do it repeatedly, showing lack of awareness, at the end, we have to address in terms of neglecting instructions or protocols. And also lack of training and knowledge. Do we have enough knowledge? Do we have enough training? Many times this is addressed in some cases, and we also can quantify. Okay, finally, another relevant part is an unsafe area, and this is addressed through housekeeping practices, improvement of them, and ownership. So the shift handover, how you leave the facility for the next shift, etc., is being also supported in terms of 5S and housekeeping and operational excellence programs. When it comes to equipment conditions, we can see that sometimes the main cause is the condition of the equipment in operation. It is the actual status. Other times we have mechanical failures or technical failures. We also see that sometime or in let's say almost 11% was a wrong design, and that almost 12% is a delivery condition. So for instance, an IBC or a drum with a pinhole or some hole that we fail to identify, and when we fill this drum or this IBC, there is an LOC. That would be an example of delivery condition. In terms of instructions and protocols, we have also some insights, unidentified hazards or wrong assessment, because we are quite critical towards our own methodologies and what we do. I mean, we don't want just to blame people. We want to put first the focus in what we have done from a safety point of view. Have we identified the hazards properly? Have we made the right assessments? Wrong or unfeasible instructions. This is also happening sometimes. We issue instructions that then they are not feasible. Even if we have implementation process and we supervise the first batches on the first task, things happen after this first supervision which was not happening during the supervision period. And then we see that sometimes it's necessary to review instructions. All this data is allowing us also to see, okay, what is the consequence and root cause relation? You see, in terms of injuries, around 70% of injuries are related to behavior, while in terms of LOCs, only 40%. So the main factor contributing to LOCs is equipment condition. Of course, this leads to review of maintenance plans and assuring reliability of the assets, etc. And last but not least, we can identify with all the rating that we did, where are the hotspots in terms of equipment, substances, structures. And this is just an overview, but the sites, the locations can really just see the data that are relevant, that is relevant for them, and really define specific actions. As a result, we see that the level of injuries or the frequency rate of injuries and LOCs is decreasing. We are in the lowest values that we had historically. So it's a very big contribution and a good improvement. So as a summary, the principles, we report data not to change, the reported data does not change the reality. It only defines our perception of it. So we want to have a lot of data so that our perception of reality is as close as the reality as possible. If that is wrong, we will set the focus in the wrong direction. And a good report does not need a lot of time. We have really an effective system. So we want to avoid the garbage in, garbage out effect. We also made a lot of progress and rose the awareness so people understand that we report to understand what's going on, not to blame anyone. We want to identify the most relevant safety topics, establish priorities, and define action. So we want to avoid this situation of just showing figures, graphs, etc. because, well, we have nothing better to say. That's all from my side. Hope you found it interesting, and I will gladly take any questions.
Thank you, Alexis, and I was very impressed by the increase in the safety performance that you were able to attain. So please, from the public, is there any question for Alexis? We prefer to make directly the question for any presentation, so it's very fresh and you can...
Yeah, no problem.
Who is the brave delegate from the public who starts? I have just a curiosity, if I may.
Yeah.
You are a multinational industry.
Yeah.
You have to confront with different international legislation and standards. Yeah. Do you believe that the different legislation may affect the performance that you attain and the distribution of the root cause or the hotspots in your plants? Or you enforce always the same standard in all plants as far as you can, clearly?
But our approach when it comes to legislation is that the legislation is the absolute minimum, because if you are not compliant, then you are illegal. So we don't want to set the bar in terms of legal requirements. That was also, let's say, a culture that we saw in some places, and not only at STAHL, in other companies, they had the same experience. Many times, to justify an investment, the first question is this legally required? Well, and if you say no, then yeah, the investment is not seen as really necessary. And for us, this is a clear the wrong approach, because as I said, legislation defines the absolute minimum. Below legislation, you are illegal. So we want to have an excellent performant. And so we didn't found any legislation which we find unreasonable in any of the countries where we operate. Typically, our standards are all above the minimum legal requirements.
Thank you. If any question, I see one question. You can write the question in the question and in the question tool. When you deploy a new tool in a big organization, there is a lot of fears about the change, especially from plants. Have you managed it? And how do you deploy this new tool in each site?
Yeah, that's a good question, because when we said we want to standardize, everyone expects that you standardize according to what they are doing. So let's say the Solomonic decision was we will implement something that nobody is using. And to challenge or to get rid of this fear of changing, we focused a lot in demonstrating that the new tool was helping the people. So we always said we don't want people to work for a tool. We want the tool to work for the people. And really they noticed very fast that with the new system, reporting was more effective, faster, more reliable, and all the information that we obtained was really helping to challenge some perceptions, both from management, middle management, and first line operators. So they really saw an improvement in understanding what was going on. And that's why we see that the frequency rate in reporting is still increasing today, not as fast as in the beginning, but we still have a monthly increase in terms of reporting. We didn't reach yet the plateau, and it's more than 1.5 years since we started the implementation. So the short answer is demonstrate to the people that new tools help them to do their work more effectively.
Thank you. And also in this way, I believe that you can enforce a sort of just culture.
Yeah.
Okay. Thank you. Now we must move. It's very interesting, and it raised some interest in the public, but now we must move to the next speaker. So I want to thank once again Alexis, and I introduce the next speaker, which is Dr. Mondie Mutegi. So please, you can wait a little, and then
hello, everybody. I hope you can hear me. My name is Mondie Mutegi. I come from Kenya, studied in Germany, and I'm working in Switzerland in a company called PELEVEN. I am focusing mainly on pressure relief and process and plant safety in general. Thank you for the opportunity to present in this talk to you all online. The topic today is going to be about expanding operational flexibility in fine chemical multipurpose reactors. In this context, multipurpose is very important because mostly you have one reactor that's really taking part in quite a number of reactions. And specifically of interest will be the new ISO 4126 standard, which is meant to enhance safety while sizing pressure relief devices, that is safety valves and rupture discs, with two-phase flow. Thank you. So I want to tell a short story. The short story goes like, because mistakes happen, layers of protection are required, and layers of protection are regulated. So we size your emergency relief system safely and sustainably. So that's the path to safety. And the intention is to really balance production, process and plant safety, and sustainability. The topic on sustainability is becoming more relevant as companies are required to do reporting. And so we ensure that we have reliable safety concepts comprehensive pressure relief design and subject to best practice and working standards. Again, beyond standards, not just meeting the minimum requirements, but really going beyond that. Okay, because mistakes happen, I'll be faster here. I just want us to look at it optically. Mistakes happen. We have heard about this. We have heard about this. But when such stuff happens, there is severe loss of good company reputation. It takes a long time, as we have seen in the previous talk, and a lot of effort to attain a good degree of safety. But we can't blink for a second, because blinking for a second can cost enormous good company reputation. And I don't know where to put this, but there is media that's actively aware, and there is the society that wants to be informed about what's happening in the society. So really avoidable process and plant safety incidents may lead to loss of life, assets, affect the environment, and they quite easily end up in news headlines. And again, company reputation is here. I don't know what price somebody can put to that. If you lose a reactor, you can say you've lost a reactor and you can put a value to it. But quantifying good company reputation or the loss of it, I submit that this is costful, very costful. Of course, loss of life is the biggest loss that one can experience, and that has and must be avoided. So to avoid all this, for example, we have the layer of protection analysis. In essence, it says like, if you have a risk, or if you know your process, you have chosen the location well, your equipment has also been set up quite well. The things that you're looking at is you have your risk. You don't want it to go outside and go to the community, for example, outside your site. So you monitor the process, you do trainings, you do alarms, you have manual instrumentations or manual interventions. And then after that, you have the safety instrumented systems. And this talk is about the pressure relief valves, which are located definitely in the area of the primary safety measures. And after that, at this point, probably there has been some loss of containment, and we switch then to the secondary measures, which include plant emergency response, community response, and so on. So the main aim is to really prevent this risk from getting outside. It doesn't matter where we are not able to do that. All of this is of primary importance. Okay, these layers of regulation of protection are regulated so that they are potent, so that they're effective. And for example, when we are looking at the pressure relief and the retainment system in the context of a pressure relief device, often the probability of area of demand is set to 1 in risk analysis, but it's only, it's set to 0.01, but it's only 0.01 if it's properly sized, considering inlet and outlet piping, selected, installed, maintained properly. So if any of these steps has not been done, it would not be prudent to give it such a high PFD, because this high PFD means that this device is reliable. So sizing in Switzerland, as in the European Union, is based on ISO 4126 when it comes to two-phase flow, which is based on DIAS, best practice, etc. And we notice that for two-phase flow, the isometry or the pipe run is very important, as it also limits capacity for the pressure relief line. If we recollect the layers of protection, we observe that the retainment systems are also supposed to be sized adequately, even if they are not specifically referred to in their standard. We need to make sure that we are winning from the reactor to a safe discharge location. So what has happened? If we look at the works of, for example, Sam Manan, documentation is also important. So you just don't size according to a standard and say, I've done it. When doing relief design, it's important to do proper documentation for two reasons. First of all, to ensure that for as long as this process unit is alive, it's adequately protected against all credible sources of overpressure, and to ensure that this information is available for interested parties. For example, if somebody is new to the company, they should be able to access this information throughout the entire operating life of a unit. So what's new? There is a new standard. It's the ISO 4126 Part 10 of 2024. And it's for sure going to, it's already doing it actually. It's revolutionizing the way we size safety valves and bursting discs. First of all, it's a first major revision in 14 years, has twice as many pages as the previous version. When it comes to what causes two-phase flow, the vessel swelling, revised assumptions, new expanded sizing model to determine the relief capacity of your pressure relief system or emergency relief system, including the associated piping to a safe discharge location. Per se, the model is consistent, and as we will see, yet numerically challenging. So for this, what you benefit from are more accurate relief area assessments with adequate safety margin, consideration of isometry, upstream and downstream. And the new standard now also covers cryostatic vessels and inclusion of liquid viscosity corrections. Of course, we'll not go through all of them. The summary is there's a new standard. It's completely new. So if you have old sizing calculations, it's worth investing in checking that everything is still okay when it comes to sizing existing safety valve and bursting disc devices. So let's jump in the world of ISO 4126 in the context of sizing pressure relief devices, be it safety valves, be it rupture discs. And the standard includes 5 sizing steps that are marked in green and orange. So you have to identify from risk analysis all plausible sizing cases. And then the standard goes directly to step 2, where you are now supposed to check if you are having two-phase flow. Then you determine the relief requirements, the mass flow rates to be discharged. Then you determine the relief capacity of the emergency relief system, that is the dischargeable mass flow rate. And after that, you check, is everything okay? Are my pipe reaction forces okay? Is my valve doing what's called fluttering, chattering, pumping, you know, the definitions of all that. So there's one step which is not implicitly or explicitly referred to in the standard, but it's important, checking that the input you've put in is right. Garbage in, garbage out, like we've had before, and also checking the substance data. And in this one, I will also focus on a very important thing that happens, the topic of overfilling. We want to produce more, so it can happen that the filling level at 20 degrees Celsius, for example, for such a reactor, is set to 85%. In this case, we can consider that, for example, we're having a loss of cooling failure for this demonstration. The medium is acetone nitrile. So the first question, even if it's not in the standard, beyond the standard, is, are we overfilling? Why would we care about overfilling? Let's think about, for example, a rupture disk. If the reactor is overfilled, one subjects the rupture disk to enormous thermal expansion forces, which could lead to fatigue and eventual premature opening of the rupture disk and unwarranted loss of contents and what we'd call emissions, etc., For a safety valve, can happen that you're losing inventory, valuable inventory, maybe cross-contaminating other places. So you really don't want to overfill your reactor, even if you want to produce more. So let's dive into an example of an old client who had what you'd call an existing facility with an installed safety valve. It's multi-purpose, and one of the scenarios identified was a physical scenario, loss of cooling. These are the parameters for the reactor: allowable working pressure of 6, sizing pressure was specified as 10% above the working pressure, internal diameter, total filling volume. I've rounded up the numbers intentionally so that it's able to have the 85% and everything else, so that the numbers are better legible. The heating jacket has a wall temperature of 250. That's the general arrangement that we're going to be looking at in this presentation. So, is there overfilling under these conditions? Is the flow two-phase flow? How much must I discharge? And is the safety valve adequately sized? We seek to answer those questions in this talk. For this, we have a tool that has the inputs being done in the usual user environment, that is Excel. And then the whole computation, the logics, modeling, validation, versioning, logics are managed in PTC MathCAD for quality management purposes, because we are dealing with the last line of defense, and it has to be of good quality. It must not fail. Remember the probability of failure of demand. We are going the extent of making sure that everything we are doing is proper. And then once the calculation is done in the PTC MathCAD, it's given to the user for interpretation. One notable thing in the new standard, it requires that those sizing actually be, sizing pressure relief devices be adequately trained and competent in the field. So you don't want to just click stuff. You need also to be knowing what you're clicking, because again, without carefully, when you calculate, you'll always get results. So you have also to be in a state to understand and interpret the results correctly. Well, the orange part helps the user to a good extent, but the user still has to be competent. Okay, don't look to the right. Let's just understand what we are dealing with. We are dealing with the reactor before. If we fill it at 85%, it's overfilled, and overfilling is detected. How is this done? Now let's look at the graphic. The y-axis is the volume of the liquid in the reactor. We see it has a maximum filling volume of 10. And if we don't consider overfilling, for example, if our tool doesn't calculate that, one would notice that, for example, at 6.6 bar gauge, it goes above the total filling volume, and one would consider this as an overfilled reactor. So in reality, if we fill, for example, 8.5 as we intended, we realize that we are going to overfill the reactor at a pressure of 3.4. Remember, we are heating the contents, the temperature is increasing and the pressure is increasing. So if we fill as intended, we overfill the reactor at 3.4 bar, and that's not good. So that's why you have to reduce the volume at 20 degrees Celsius to a range of about 8.2, so that really you don't or you reduce the volume to at least 8.2 cubic meters, so that you have your filling point at the sizing pressure. Of course, this is at the edge. You need to reduce more. And in the next example, or in the actual example, we reduce the volume to 80% so that we are away from this point we are seeing here. So reduce the volume by more than 300 liters, and our chosen point is 80%, 8 cubic meters. The calculation tool will warn the user when overfilling is detected. It will tell them, you wanted to fill to 85%. No, it's not possible. The maximum filling volume is 8.1, and it will warn them that it's overfilled, and it will tell him, okay, you're two-phase flow. So the user is informed optically, so they don't have a chance to just move on because they were not able to interpret the data per se. Then for the example, now we go with a lower filling volume. And again, we go to the tool and we see here is how now you predict two-phase flow. The standard has got, I don't know, I hope some of you have looked at it. There's a battalion of equations, very many equations. And one of the mammograms that are present there is this one. It says, in essence, that 4 different conditions, turbulent and bubbly, for different parameters. If you are below, let's look at the turbulent one, which is valid for this case. If you are below, or if your operation point is below this continuous green line, you are going to discharge gas or vapor, or more precisely vapor. And if you're above it, as we can see in the purple point, we are two-phase. So again, the user doesn't have to get into the confusion of what parameter do I use when. The logic in the program is able to predict that it's two-phase, and it will guide them based on the inputted parameter and the logic that's included in the standard. It will be able to guide the user to the right curve to use technically. So what we are seeing here is the back end, and the front end is this, and the user will be informed about which models have been used. Okay, away from that, we now know that the flow is two-phase. How much should we discharge? And what's causing the trouble in the reactor? It's heat input. And when we look at the curve the curve to the right, we observe that, for example, we have the specific heat input. That means is the heat input because of external heating in kilowatt by kilogram. And here we have the sizing temperature, or as we are heating, and as we are heating, we are getting to the saturation point. And we see that these two curves, considering the sizing temperature and the associated sizing pressure, they have a similar flow. And well, it's one can work with temperature, one can work with pressure. But since pressure is mostly what we are protecting against, over pressure, we continue in this part. So we see that for external heating, as you increase the pressure, as you reduce the heat input because the sizing pressure goes in, and the differential temperature between the wall and the contents reduces. Therefore, the heat input goes down. And for the reaction, you have an exothermic reaction, which is exponential. Therefore, the mass flow rate increases. So I don't want us to understand these equations. I just want us to make one observation, that you have equations for external heating, for reactive systems, one-phase flow, and for reactive systems tempered. And one observation is, if we give the reactor a constant amount of heat, one will have to discharge more for external heating than for reactive cases. Why? For reactive cases, part of the heat is, or there is evaporative cooling. That means you're bubbling and there is evaporative cooling. That's why some of the heat is not per se used to create mass flow rates. So how do we validate equations? There is a work by Leon of 1986. This would be this equation, and there is the standard. Again, don't focus on the equations, just focus on, for example, the trend of the mass flow rate that has to be discharged, the relief requirements. For external heating, we come to the conclusion that two equations developed by two people with two control rooms come to similar equations. for external heating, as well as for the reactive tempered equations, which is something you want to see when you're modeling and validating the model. So this is good. Next step, away from that, we are now looking at how do we improve the capex? Again, the same equations, mass flow rate to be discharged, and then the sizing pressure. We have the tempered Leon and the tempered ISO, and then we have the external heating in green. So in this case, for the sizing point, we would have to discharge a mass flow rate of 29 kilogram per second. And this is where, if you're sizing equations and you're not seeing this, you are not able to improve your capex. So if you size now at this point, you find that you are able now to cover the external heating and the chemical reaction for your multipurpose plant in one. Again, the tool gives you this information and calculates a number of mass flow rates and selects the one that's valid for your system for you. Okay, and in the interest of time, we move to the next time. Again, we are not looking at equations. Just tell you that to bring the point home that the equations in the standard require a lot of computation and they're complicated. But let's now look at the vent line system. We are looking at a piping system with 6 segments, and the safety valve is installed in segment number 3, and this is the exit. And for example, if you look at the nozzle, this is the operating point, this is the choking point, and we would observe that this point is not choked. This is the 55%. If we move to the safety valve, we see that the operating point is at the choking point. That's why we attain choking point. And if we look at the next component, which would be the exit of the pipe, we also have choking. So it shows that choking can happen anywhere in the vent line system, and it's good to investigate it. So if you have choking at the safety valve, don't just assume you are done. You have to match through the piping system, and this tool does this for us. So I'll jump to the conclusions so that we don't overshoot. We have seen that if we apply the current standard, it's possible to improve your capital expenditure. So when you go and calculate, don't be happy if you calculate and you get results just by user input in a few fields. It's good to look deeper because you're saving a lot of money. For example, if you are able to make a decision, you're not going to install a DN150 over 30 meters, you require maybe DN150 for the first 10 meters and DN250 later. And also for the safety valve, you are able to adjust your safety valve for exactly what you need. And this is the benefits of the work that we continue to do. And we are glad if you get in touch with us. If you have questions, questions are always good. We are happy to answer your questions and to attain next level enhancement of process safety in the area of emergency relief. That would be the end of my presentation. I'm happy to have any questions.
Thank you, Mondie, for your very technical and detailed presentation. Now we have room for some questions from the public. I remember you can access the bar at the bottom of your screen. We received a comment from Jean-Luc Revel, who I thank, and he tells us whether the probability of failure of demand of 0.01 also integrates the management part.
Well, there has been a white paper that was released by Deshema, and I'm sure it's because if you're really managing the installation, you're managing the sizing, you're managing the selection. So overall that it's the management, and management is really what determines safety in a site. So yeah, the management has to support all that. If it doesn't work as well as it should.
Thank you. And thank you also for showing the new opportunities that are posed by the newly enforced legislation and the new insights, let me say, the safety aspects of this important technical aspect of our reactors.
And maybe a feedback to that is, if really one gets into some hindrance while implementing that standard, don't just assume that you're right. Kindly seek guidance, because observations are that one can size wrong, and that doesn't help safety. Thank you very much, Bruno.
Thank you also for this this last comment and warning. Thank you. So we can move to the next speaker, and so give the room to the next one. And please, you can upload your presentation.
Thank you, Bruno.
We have Professor Alessandro Tugnoli from the Chemical Engineering Department of Bologna.
Thank you. I hope you can all see the presentation correctly.
Yes, we see. Thank you.
Excellent. So my talk today is going to be about safety challenges in the future implementation of a value chain for liquid hydrogen. What is liquid hydrogen, of course, is the first question. Well, liquid hydrogen is the liquid state of hydrogen that we have at room pressure at 20 Kelvin, so cryogenic temperature. Working at this in this condition is interesting because here we can achieve relatively high densities for hydrogen, so we can put more hydrogen in less space, let's say. And just as a reference, if you compare that with compressed hydrogen at room temperature, the density at 600 bars is almost half of that. So makes sense to store hydrogen in this condition. However, density are still quite low. We are talking about 70 kilograms per cubic meter. What are the inherent hazards of hydrogen in this condition? Well, we still have the same hazard we would have in gas condition, so potential for combustion. Actually, quite easy ignition. The ignition energy of hydrogen is known to be at least one order of magnitude less than the one of hydrocarbon vapors. But beside that, we are also in cryogenic temperature, very low temperature, 20 Kelvin, as I mentioned. So that adds a new form of inherent hazard. Beside that, there are the issue with material compatibility. Hydrogen is already known to cause some embrittlement phenomena by itself, by its interaction with metals. Here, at the low temperature, that of course makes embrittlement even more critical, especially for materials that have not been designed to the scope. So why do we want to use liquid hydrogen? Well, the idea is to have available an energy vector with, as I mentioned before, quite high energy density. Hydrogen has been extensively proposed as a future energy vector. We need energy vectors because the exploitation of some sources of renewable energy is non-programmable, so we need to store to match, let's say, availability of the energy with the demand of the energy. But we need also to be able to transport this energy, possibly long distance, and therefore these kind of vectors are of interest. They are also interesting when the final application of the energy is on a mobile vehicle, for example, an heavy-duty truck, because that's what we are really familiar with oil-derived fuels, basically, to store energy on the vehicle and let it propel it. Liquid hydrogen is not an entirely new technology. It has been exploited for some decades, several decades, in the space exploration field. But that's a very specific field, and the needs and technology we will have applying it for a more widespread use will be different. So there's some experience, but cannot be immediately expanded to the future setup. Quite prominently, there is liquefied natural gas, so that is a cryogenic fuel, which may have a comparable value chain. However, we have to keep in mind, on one side, the temperature are different. There's almost 100 degree Kelvin difference in the temperature, being the one of liquid hydrogen much lower. And also, the size of the equipment that we have is expected to be much bigger, especially for storage. The energy density, the energy per unit volume available from combustion is almost half of the one of LNG. So we expect double the number of tanks, or tanks double the size, for example. The value chain can actually be quite well compared with the one of LNG, the expected value chain. We have the classic phases of production, liquefaction, shipping. The shipping is expected to occur mainly on carriers at sea. But then we have phases of distribution and use, which may go into areas where we have general population. While all the other phases, they may be restricted to industrial zone where management of risk is already a practice, let's say. In the public areas, we are introducing a new hazardous material with specific features that have to be properly considered. This is, of course, under the idea to use hydrogen directly as a fuel on the final user vehicle, as it has been currently proposed for trucks and boats, but it's also proposed for the future application in the aviation industry. Now, what will be the open safety issues? What I'm going to talk about in my presentation? Well, basically, the first series of issues will present a concern with the description of the hazards present in this field. There's no yet complete understanding of the fundamentals underlie some of the accident scenarios that we may expect. We have a lack of data, especially experimental data, and models that are out there that can be proposed for this application. Because of this lack of data, they are not fully validated. More in general, in the risk assessment of these technologies, we have to face the fact that there are new technology, emerging technology, for which there's no unlimited past experience, and that hinders a number of consideration in the risk evaluation and management. And finally, we have to consider the regulatory work that is framework that is not yet established. Now, when I'm talking about new technology, let's see how large-scale storage is implemented so far in the space industry. The main way to store large quantities of liquid nitrogen is by tanks that are spherical in form, that reduces the surface per unit volume, and that they are built with a double layer with vacuum insulation in between. So there's very low pressure, a few pascals, and there may be some filler which limit the radiative heat transfer. For example, multi-layer insulations. Now, the construction of these tanks, even if we have experience of decades, is known to be very costly, very complex, long time to market, very low failure tolerance on something that can get wrong. And plus, the current maximum sizes we have are much lower than the one that we would expect for the future application, that are an order of magnitude higher than even the current designs. So this is not expected to be the way to go, and that's why research went for new design, new concepts. For example, a very promising concept is to move out of spheres and go to prismatic tanks, similarly to what was done in the LNG industry. That way, the construction of tank allows to be more similar, let's say, to tanks that we have experience in building, and possibly cheaper in terms of costs. That, however, requires to implement new solution. For example, a solution recently under development within the Nicola project, which is a EU-funded project, is the one of vacuum insulating panels, using pre-assembled panels where you have a filler, you have an envelope, and you have vacuum basically in the porous part of the filler. So you can assemble these bricks of vacuum, basically, you stack them, and you make your insulation in a way that shall make more efficient and easier construction of this kind of system. However, this is an entirely new concept. We have no previous experience of this. And so you can understand that getting data on reliability long term of this, on behavior in anomalous condition, is critical for the safety assessment. I made the example of the storage that we expect to have in large quantities if we want to distribute this capillary, but there's also the issue of the let's say distribution station, like for example a fuel station for an heavy-duty truck. Here, we need to transfer our liquid hydrogen from the storage at the station to the vessel on the final user. And a similar problem we will face, for example, of transferring for restocking the fuel station, so bunkering or in bunkering operation for fueling ships. And well, these operations are operations that are expected at least to be carried out partially with manual action, and they are very complex. You need to purge all the connectors. You need to make sure the cooling down is done correctly to prevent formation of ice and so on. And as we know, in any complex operation, there's potential for human error. Especially, and that's not something new. We don't know how to tackle in general. We know how to manage human reliability in safety critical systems, but implementing it in these new systems that have to be designed, systems that have to be fully understood for their dynamic behavior, is of course a critical aspect in the implementation and achievement of safety. Also, CMOPs, another thing that we are already used to study, have to be explored in this field, because while you're carrying out a fueling operation, you may have other fueling operation going on, or you may have other operation like loading loads on the ferry that you are fueling or something like that. So that's something that, again, has to be translated in this field. Going back to the more closely to the risk assessment, there's an issue about the accident scenario that we may expect from this kind of system. Here I did a little exercise. I asked someone that was not entirely expert in the hydrogen field to implement a standard tool for identifying hazard, for building an inventory with a reference to a large-scale tank of hydrogen and a large atmospheric tank. And you see here the scenarios that were proposed. We have, for example, pool fire. Well, that makes sense. You are storing a liquid, you spill a large quantity of liquid. Upon ignition, relatively soon ignition, you may have something that looks like a pool fire. Well, we don't know if this is the case for liquid hydrogen. There's no experiments of such large scale releases. There are experiments with spills, but the pool size is still quite limited. So we don't know what happens really for very, very large scale. And this can be applied also to other scenarios. So even for the scenarios that are conventional scenarios for other hazardous material, which are similar characteristic to the one of hydrogen, well, we don't know how they behave in case of hydrogen. And of course, that hinders also the development of consequence model. Are they valid for this scenario? Are we trying to extrapolate from what we know too much? That's surely an open question. But beside the scenarios that are, let's say, shared with other flammable materials, here there are also specific scenarios due, for example, to the particular condition in which we are operating. At the temperature of liquid hydrogen, the main components of air, oxygen and nitrogen, will condense and possibly freeze. Nitrogen will freeze for sure. And that creates, of course, a form of solid, of ice, which affects the behavior of spilled nitrogen. And in particular, there's a concern about oxygen, because if you bring oxygen to condensate phase, you unlock the potential for condensate phase explosion between the oxygen, the liquid oxygen, and the liquid nitrogen, liquid hydrogen. And that kind of event, we don't know if it's practically possible, if the mass transfer allows that, basically, in this spill condition. In fact, there are tests going on as part of the ELVIS project, because the phenomenon possibly occurred once during an experiment in the past at the HSC, but was not in controlled conditions, so it's not clear what exactly was going on. So we need more tests, as the one that are planned within the next year, to understand if this is practically possible or not. But this phenomenon of air condensation and freezing also affects our understanding of the hazards that can be the hazards and the mechanism of accident evolution that can be in the full three part of a boat eye. So, for example, in some tanks at NASA, there was an ingress of air into the vacuum insulation, which led to formation of ice, and that formation of ice created ice from nitrogen and oxygen, so solid air, and that created a thermal bridging. The thermal bridging damaged the equipment itself, because it brought some areas that were not supposed to be a cryogenic condition into cryogenic condition, causing cracks and so on. So a mechanism that, if uncontrolled, may lead to overpressurization, severe overpressurization of the tanks. So understanding of all these phenomena is obviously interesting. It is obviously a key for safety. There are some scenarios specific of other cryogenic fluid that we have been wondering for a while if they are possible, or at least likely, also for liquid hydrogen. I'm referring, for example, to the rapid phase transition. This is the sudden explosive evaporation of a cryogenic fluid when energy is available from contact with another surface. And we know that occurs for LNG in contact with water. So the question has been, is that the case also for hydrogen, for liquid hydrogen? Well, again, it's important to carry out tests and real scale tests, because thanks to the SHIFT project, a Norwegian project that was carried out a few years ago, we have now testing that says that at least over 24 tests that were carried out, the rapid phase transition did not occur, so seem not to be a highly likelihood phenomenon at least. However, thanks to this test, we know that the ignition in this kind of situation is extremely likely. And that's probably due to corona effects on ice crystals that are created during the spill. And again, that's something that obviously in risk assessment has to be taken into account, and that we were able to learn only through deepening also the experimental understanding of the phenomenon. Jets. If you store it in large tanks at ambient pressure, of course, there's no potential for jets, but for the small storages, some degrees of pressurization is expected during operation. And so jets can be formed. Now, what's the effect of these jets if not ignited the impact material that are not designed for hydrogen? Well, we don't have protocol yet for testing that. We don't have standard yet for testing that. what about if they are ignited? Well, in that case, it seems the behavior is similar to gaseous hydrogen jet. The vaporization occurs relatively quickly. And so we can borrow on what we learn from the development of models for gaseous hydrogen tests. But yet also on those models, there's a lot of open question, for example, about the interaction of these jets with surfaces, the potential heat transfer to these surfaces, the potential damage that can have from this sort of jet, from the momentum of this sort of jet, fireproofing located on surfaces that you may want to protect. So it's something that presents evidently quite large gaps of knowledge. If you think a small vessel, it may be possible that they find themselves in an external fashion area. And that may damage the current insulation systems that are designed to prevent input heat flux in normal operating condition, but not in fire condition. Here I'm presenting some results from a study of some colleagues that choose to go for exploring this by using data collected at small scale. Again, collection of data is important, but even the preparation of some preliminary models that rely on those data to try to simulate what is the expected behavior of tanks, even without doing a full-scale test, may help us understanding the potential for this phenomena and possibly also to design better tests for fully exploring them. When we model this phenomena, we have also to take into consideration that on small scale, accident phenomena may evolve very quickly. The dynamic nature of this has to be taken into account during modeling. So that makes, of course, CFD modeling very promising. But also in developing engineering tools, integral models, we have to be able to tune them, keeping this kind of effects in mind. About risk assessment, of course, we have to face also the fact that lack of knowledge about new technologies makes very critical estimation of some parameters like release frequencies, leak frequencies, that are fundamental for quantitative risk assessment strategies. On that note, there have been attempts to fill the gap. For example, here you see the results of a study from Sandia that used the Bayesian model to extrapolate basically the information available from leakage frequency in the oil and gas industry to envisage the hydrogen industry. Well, of course, the quality of this extrapolation is based on the quality of data that you have. And as very few data are available for hydrogen, one shall be very careful in implementing this result, especially because they show, as you see in this diagram, a behavior that is very different than the one of the system that we know, a few orders of magnitude lower as frequency of release. Is that due to the high standard of these components, or is that done to underreporting of this kind of events? Well, that's, of course, something to closely monitor and explore in the future. Finally, regulations and codes. Working in a context in which we want to implement in the real life with the industrial applications, the liquid hydrogen, we need to be compliant with the regulation. Well, the regulations are currently in many countries still under development. Up to now, they have been focusing mainly on gaseous hydrogen, and the feeling is that the regulation on liquid hydrogen will just be an extension of that, will follow some similar rule with adaptation. So, for example, the approach of safety distances for land use planning will be followed also in this case. Obviously, safety distance have to be based on consideration on modeling of potential consequences that are affected by all the concerns and gap of knowledge that I mentioned before. Beside regulatory body, also standardization, technical norms, they are working actively on this field. As we know, this is a common approach, the one based on standard for widespread mass-produced systems, as will be, for example, the tank of hydrogen vehicles. Well, there's a significant effort, and there are standards now currently under development for that. But again, they are based on the current knowledge. Now, let me just mention, as a concluding remark, another issue that is the integration, together with safety consideration, of the security consideration. This is not specific for liquid hydrogen, but the fact that we are setting up a new system for the value chain of liquid hydrogen, that we are setting up new rules for managing the safety of it, can give the opportunity to integrate in these rules also security consideration. It is well known that potential conflict may arise between safety and security, and so putting them together will be beneficial, and this is the opportunity. And I'm talking about physical security as well as the frontier aspect of cybersecurity. Systems are more and more interconnected to the general net, and so these kind of cyber attacks may be critical. Finally, leading to conclusion, let me wrap up. The development of future chain for liquid hydrogen brings hazards next to the population, increasing the concerns about safety and about the acceptability of this technology. We still have gaps in the understanding even of the fundamental of the scenarios involved. There's a lot of effort from the scientific community and the industry to fill these gaps, but they still exist. More extensive testing and collection of data is important. It is expected to help from this respect to provide validation of the model and to support the development or regulation and standards that can make this value chain definitely safe. Thank you for your attention, and I'm available for questions.
Thank you, Alessandro, for your complete presentation regarding the challenges connected to liquid hydrogen. So unluckily we are a little late, so I invite the following two speakers to strictly respect the time, and I must go to the next speaker, who is Dr. Rustam Abubakirov, who is Master of Science in Offshore Engineering University of Bologna, and he will report about examining safety risks of ammonia-fueled ships. So please, Rustam, you can start your presentation.
Yep, I hope that you can hear me and
yes.
You can see my PowerPoint, which will be better now. Yep. First of all, thank you so much for your kind introduction. My name is Rustam, and I work with Dr. Ming Yang at TU Delft at the section of Safety and Security Science, and we investigate the safety risks of ammonia-fueled ships and how to deal with this. Well, this project is our own research project, is part of the larger Ammonia Drive one, and Ammonia Drive consortium unites 7 Dutch research institutes and 15 companies, pretty much across the entire value chain of the future ammonia operations. And we together investigate the combinations of internal combustion engines and solid oxide fuel cells for propulsion and generation on board of the vessels, of course. And given that flammability of ammonia is the issue, we utilize the hydrogen as a promoter fuel in our concept. So it will be hydrogen produced on board from the ammonia itself. And this will allow us to go single fuel without any additional fuel on board there is no carbon in this chain, so it will be completely pollution-free. But what is important for us is that by utilizing solid oxide fuel cell, we'll employ this power plant at the high efficiencies, which is attractive for our maritime partners. But of course, safety is critical on our agenda. And particularly in our research, we consider all ammonia fuel technologies, including so-called ammonia diesel ones, because regardless whether it's solid oxide fuel cell or not on board, the issues are practically the same and remain unchanged. And now today I will provide you an overview of the risks which we foresee with adoption of ammonia fuel technologies. And then I will cover some implications for the design. And last but not least, I would like to touch the topic of cost effectiveness, because when we discuss the decarbonization technologies, except those ones that directly go into grid, generally we talk about low or if not negative profit margins, and we don't want we don't want safety to be the cost for that. But about that a bit later. Yeah, ammonia is attractive for us because of its relatively high energy density. I mean, it is still the highest one among the zero carbon fuels, higher than hydrogen, higher than lithium, higher than batteries, but of course it's lower than any hydrocarbon fuels. This will, I mean, in terms of the decarbonization agenda, this is attractive for us. But among the all fuels listed here, ammonia is the only substance which is under the normal conditions is a toxic gas. And given that flammability of ammonia, I list some numbers here, is somewhat of a less issue. It has very high ignition energy. This is 2 orders of magnitude higher than hydrogen listed, and it will be almost an order of magnitude higher than any hydrocarbon. But for us, the toxicity, which comes as a first issue. And when we talk about these concentrations, ammonia will become rapidly fatal at about 3,000 ppm, 5,000 ppm. So we can factor out time there. So this is 2-3 times lower than flammability limit of hydrogen, and an order of magnitude lower than any hydrocarbon fuel. And for us, this means that the design of the fuel systems and design of the safety systems around that will be shifted from flammability driven to the toxicity driven, and we find this shift to be quite fundamental. Of course, chemical industry utilizes a lot of ammonia, and there are substances which are severely more toxic in the world, but for us, the context matter. First of all, the container vessel or bulk carrier is not operated by a chemical company. So we're talking about quite different level of expertise, of local expertise. And second is we find safety regulations in the maritime to be quite inertial. They are centralized. We have an International Maritime Organization, which is central in policy making regarding safety. And these regulations are very prescriptive even for European chemical industry, in my opinion, which is not a disadvantage by itself, because these prescriptive regulations, they codify the experience with flammable substances over century, I would say, of operations. But, and we find in this context, this standard inscription on the vessels to be quite symbolic. But when we rapidly introduce the substance, the fuel, which carries drastically different properties, we find this to be quite problematic. And about the regulations, a couple of words. For us, the IGF code is central. It's international code, and this allows us as researchers to be quite precise in discussion of the safety measures. We can discuss which safety measure we question or which can we propose for that. And as for now, this code includes only requirements for the natural gas, only technical requirements for natural gas. But in the next months, this will be changed. But so far, there is still the principle of alternative design, which requires the shipbuilders to demonstrate that the safety level, that the risk level of the ammonia vessel is at most equivalent to the safety level of the natural gas. IGF was primarily written for the natural gas, and then it acts as a benchmark for us. And this principle of alternative design, in some sense, it is a risk acceptance criterion for us. And while the IGF does not list technical requirements for ammonia, still there are pretty old classification societies which releases their requirements for the ammonia-fueled vessels, and requirements they look pretty much similar because, well, LNG operations are there for decades, and a lot of experience has been codified there. So what we see there is that, yes, we see the requirement for the dedicated spaces, so fuel systems should be separated from any other. If it is dedicated space, it should be gas tight. If it's not, if the elements of the fuel systems are outside the spaces, it should be all in double piping. This double piping should be either pressurized or ventilated. There are multiple requirements for the rapid gas detection and isolation. But what we see new there is requirements for the emergency ventilation, for the water mist. We see even more requirements for rapid gas detection. And the question which we asked ourselves in our research is that, look, we have the new requirements which look very much similar to the IGF code written for the natural gas. And now here I highlight the measures which are new for the ammonia. So if we have requirements, minimal requirements for natural gas, and we apply these measures, will it be safe as before? And to answer that, we developed some QRA models. Here I present LSAR distribution, location-specific individual risk, for several ammonia concepts. They vary in types of storage and in the supply principles, in which phase, for which types of the engine ammonia is supplied, whether it's gaseous or liquid. And then here are three ammonia concepts, and then we compare the risk to the risk of the LNG use. And returning to my question, whether it will be as safe as before, the answer will depend. For the deck officers, for the deck crew who don't interact with the fuel systems very much, the risk will be the same, and we can claim this to be safe. LNG by itself is a success story because keeping the fuel systems inside the compartments, it prevents the risk from propagating beyond it, but at the same time, accommodating more complex systems with a more hazardous substance inside the confined space elevate the risk for the ammonia. You see that the risk for the ammonia inside the fuel preparation room here is 1 to 2 orders of magnitude higher than the risk of LNG fuel preparation room. And this creates this rise in location-specific risks naturally transfers to individual risk per annum for the engineering crew, for the engineering ratings that who will service these systems. And to arrive to these conclusions, I mean, we don't find that the advanced QRA is needed. The reasons are quite simple. First, I can list 3 of them. First, to fuel the same vessel, we need more ammonia because of its lower energy density. The increase is about 50% compared to LNG. Second, we don't need ignition in order for the hazardous cloud to cause some troubles. of course, then with toxicity effects, time plays role, but still they don't balance each other. And third is that all the measures which we discussed, they deal with the removal of ammonia from the compartment. So it's decontamination measures. And what we found that quite specifically for the fuel preparation rooms and for the smaller engine rooms, that that simple model, assuming a complete mixing of the gas inside it, will provide a nice proxy for estimation of the measures inside. And imagine that that we have a substance which is hazardous at concentrations at around 90 times lower than before, and now we just require the ventilation to be 1.52 times higher. Will it help? I will leave this answer open, but there are many doubts for that, and therefore we identify the increased risk in fuel preparation room in the smaller engine rooms as our primary concern. There are also other issues with sensitive cases of the use of these vessels, but this is more a question for regulators, whether these vessels should be allowed for the densely populated ports. Still, these cases can be evaluated on a case-by-case basis. What we identify as the prime issue is the risk for the engineering crew. And in our second study, we tried to approach this problem with the question, what can we do for that? And here we had the case of the ammonia engine room. We had 3 ammonia engines, which are used as generators. We had gas valve units, enclosure type gas valve units inside the engine room. And in order to answer what can we do for this, what can we do in order to reduce the risks, we propose to think conceptually first, because in a form of a causal diagram, as described, as presented here, for us the probability of fatality due to intoxication is of interest, and this fatality is due to a leak of ammonia, a random variable with 2 outcomes. And the leak itself is guided by any random factors which are definitely beyond our control. And with a certain probability, depending on the severity of consequences, leak will escalate to a fatality. And here we had barriers, performance of the barriers, which by manipulating which we this likelihood of a leak escalating into fatality can be modified, but as our QRA model shows, this can be true, but not in the concentrations of our interest. So therefore, we don't see opportunity in enhancing the performance of the barrier further, and we don't see this as a viable risk mitigation option for ammonia-fueled ships. But what instead is that what we have instead are another variable, let's say human-machine interaction, here, which we can control. It may sound banal, but in order to have a fatality inside the confined space, a human must be present inside it first. So it needs to interact physically with the hazardous machinery. And by manipulating the probability or the frequency of these interactions, or trying to reorganize how these interactions are performed, we can either change this probability of I being interactive, or how likely each interaction is going to lead to a fatality or to a leak. Of course, interaction is not a standalone variable. It depends on the performance of a system, because why someone needs to go inside the engine room is because there are maybe some troubles with the engine which needs to be fixed. So therefore, change in performance calls the change in interaction, and future performance of a system depends whether the interaction has been successful. And therefore, for the effective control, we need to control both. And yes, the interactions may sound quite abstract, and we had a study with the operator of a similar gas-fueled engines. There are many types of interactions inside the engine room. We counted 600 different types of them, but many of them can be grouped. A crew needs to be there for the start of the engine, for the monitoring, for the inspection, also for the maintenance, for the service of the auxiliary systems, which are usually inside the same compartment. So what I want to say is that grouping and doing the risk assessment per interaction basis is still feasible. And just jumping straight to the results, what we want for the engine rooms, for the ammonia-fueled engine rooms, is that we want further compartmentalization, division of compartment into smaller spaces. This will reduce exposure, for example, working with auxiliary systems from the hazards coming from the engines. This can also be helpful for the maintenance. We want all auxiliary systems to be located outside as well. There is also potential with CCTVs, but we are quite cautious about that. But what I want to say is that the largest risk reduction opportunities with ammonia-fueled vessels, we see in the higher maintainability of the systems, particularly the engines, higher reliability of the components of the engines and the fuel supply systems. We want condition-based maintenance for these systems, and there is also quite active discussion on the lubricating oils for the ammonia engines. Why do we emphasize these measures? Is because in overall, we want to have less reasons for the crew to come inside this hazardous space and interact this. And these measures, in our estimations, are the most effective ones. And here is a list of full measures, which interest reader can go through. And our claim is that the effectiveness of these measures increases from the left to the right. So we want to emphasize this Class P and some of the Class I measures for the future ammonia vessels. I understand that emphasizing maintainability or reliability of the systems fits into this safety too, also fits into resilience agenda. But the reason why I believe that this can be helpful is simply the cost effectiveness. Of course, it's arguable, but an X-selector below the ceiling of the vessel, of the engine room, doesn't create any business value for the company except for safety. Meanwhile, investing in the reliability of the engine components, specific sensors, for example, we find them troublesome, is advantages for some other reasons as well. So extra gas detector, except of risk reduction, of course, at least in the eyes of the operators, and relating risk and the reputation of the company, of course, it requires some advanced safety culture in the company. But still, this is a linear dependency. But with these Class P and Class I measures, we want to explore these additional agendas. And our belief is that by searching for these additional agendas, for these additional economic benefits, which will reflect in a cash flow of the operations, we can subtract some of the costs of ours. We can subtract these economic benefits from the costs of these measures. So therefore, we can make the risk reduction per the unit of risk more cost effective. I understand that this may sound as like a bit of horse trading to search for other agendas inside the safety measures, but our belief is quite simple, is that, well, we're in a decarbonization projects, we're in a quite challenging economic situation, and more attractive measures we can propose by prioritizing the measures which create these tangible burdens. We can propose, we can make safety more attractive. And by proposing more attractive of safety measures, there is higher chances that some of them will be implemented. And this is the second implication this is the direction which these projects force us to think to. And conclusions, I think, will be quite self-repeating. Yeah, the risks inside the ammonia spaces is quite high and is concerning. We expect the risks to be 1 to 1.5 orders of magnitude higher for the engineering crew, which violates the principle of alternative design. We see the major risk reduction opportunities in measures which enhance reliability, autonomy, maintainability, also the integrity of the systems. And we also see a large rationale in promoting these solutions, fostering on reliability from the cost effectiveness perspective. But cost effectiveness is the topic which is very sparsely covered in academic literature, and definitely a lot of research is still needed. Thank you very much.
Thank you for your presentation, Rustam. It was really interesting and it's a hot topic, let me say. And we have just time for a very quick question from the public, if any. You can write it in the menu. Do you touch a little, just a comment, the point of a possible use in cruise ship? And now I believe that there is a strong debate about the possibility of utilizing instead methanol, which poses less hazards. Do you believe that in the future will it be possible to rely on ammonia, or in our horizon?
Well, this issue solely depends on the integrity of the storage tanks, because cruise vessel is a quite large vessel, and only in the storage tanks there is enough inventory in order to hurt the passengers. And this will depend how the development of the storage tanks, where it will go. There are this Type C technology, there is Type A, this prismatic tanks, but also there are membrane tanks, which are quite interesting. But unfortunately, there is so few empirical evidence on that in terms of their integrity. But I'm quite optimistic about that.
Thank you so much also for your comments. And now we are going to end this spotlight talk with a presentation that will be given by Nicola Paltrinieri from NTNU. He will cover the issue on how is artificial intelligence used for safety and reliability across industry. So please, Nicola, you can start your presentation.
So I believe you can see my slides in presentation mode now.
No, good.
So thank you, Bruno, for the introduction. The title was already read by Bruno. My name is Nicola Paltrinieri. I am a professor at the Department of Mechanical and Industrial Engineering at NTNU in Norway. And I will be talking about artificial intelligence uses for safety and reliability across industry. I will also give a focus on the energy industry, renewable energy industry, hydrogen industry, for example, given the overall topic of the day. I start with, let me reduce this. I start with these two, let's say, pictures of two different people that years ago gave, let's say, statements in different forms on artificial intelligence with, let's say, opposite messages. The one on the left is Professor Dickman from University of Colorado, who was very optimistic on the use of artificial intelligence for risk analysis, for example. So the use of machine learning, cognitive sciences in order to improve and advance risk analysis. On the right, instead, well, you can read it here. You probably recognize this, the chess master Kasparov, that in 1997 lost a game against Deep Blue, that was considered, say, the first example of artificial intelligence, a program that was coded to play chess and won against the number one at the time. And Kasparov, of course, well, probably was not very happy of the result. He said that Deep Blue was as intelligent as an alarm clock because it was programmed to do specific things, but the real intelligence is not there. Where are we in these two extremes? Well, first, probably before we try to at least give some examples to answer this question, we should define artificial intelligence. So intelligence that is demonstrated by machines, and we can divide it into subfields, subtopics based on, say, technical considerations. There is artificial intelligence for robotics. There is artificial intelligence for artificial cognition, machine learning, or it is focusing, let's say, defined based on its tools, logic tools, but also you've heard of it quite a few times, I'm sure, artificial neural networks that are now pretty popular. We got here through different phases, I must say. There has been a few years ago a period of let's say focus on Industry 4.0, on collecting as much information as possible on different aspects of our processes in industry, collecting, for example, indicators, quantitative indicators that were able to describe the performance of different aspects, different technological system in our industry. And in particular, I give here some examples of some, let's say, logic hierarchical schemes of indicators, indicator collection, indicator aggregation for the assessment of safety measure performance, or better, safety barrier performance. And from time to time, I also want to say that I report some of the references that I used, or at least some of my past work on these topics. Here, for example, at the very bottom of the slide, you see a reference to a book on dynamic risk analysis that was addressing this very topic. Even on in the regulation level, reference to the, let's say, the potential, the opportunity to collect information, data, indicators could be found. For example, when we talk about the Seveso III regulations on the handling of hazardous substances, Seveso III regulations that I remind you, they are issued by the European Union. But they are implemented by the countries of the European Union with different timing and different, let's say, in different forms. This aspect of collecting and monitoring quantitative indicators is present more or less across Europe. I say more or less because here I compare 4 countries that at the time when I did this review were all in the European Union. So I start from the United Kingdom, where common regulations required, let's say, the reporting of injuries, diseases, dangerous occurrences in a database called READOR. France instead was not explicit in the regulations and was not explicitly saying let's collect quantitative indicators to assess safety performances, but there are the results of a project by INRIS showing the need to identify them and collect them. Italy, instead, in the legislative decree that implemented the Seveso regulations, refers to safety performance monitoring, while Norway, once again, does not explicitly refer to indicators, but one of the most important research institute in the country, SINTEF, at the time issued a report showing how useful this monitoring would be. So across Europe, there was, let's say, the push for collecting more information, more data in order to describe our systems in general, but also from a safety point of view. Can this information be used to make the machine intelligent? So let's say, to feed the computer and get, let's say, better processed information. Here I show, well, way too many examples. Would probably focus on some of them. But I show 6 examples because they somehow represent different types of applications of AI, machine learning, or anyway, some forms of machine learning. And I also mention say quotation that says there ain't no such thing as free lunch, because we know that we cannot really generalize with the machine learning approach. There are some, its optimization for the purpose is so sometimes, let's say, specific and complex, especially, I must say, from someone that has an education in chemical engineering, that each case, each application is somehow by itself, okay, and requires ad hoc optimization. I once again report the references for each of these applications. And let's say I start with the first one that analyzed the MIDAS database, a database that was discontinued at the beginning of 2000, but is particularly good because it collects almost 9,000 hazardous events. And based on the information in that database, we try to predict, let's say, consequence classes, I must say. And we had some results, some good, some less good, but I must say that the results were interesting, in particular based on the conclusions that I will take today. Another application was taken for offshore, for an offshore drilling rig, and here things were a bit more complicated because we addressed indicators describing socio-technical systems, so also operations carried out by humans, operators. However, I must say that in this case, the data used was synthetic, okay? So even if we put a lot of care in producing such synthetic data, a machine learning approach somehow is producing better results in the moment in which is fed with synthetic data. The idea here was to predict the damage frequency in the activity of a drilling rig, okay? And we showed quite good results in this case too, with the limitations that I mentioned. This other example is about alarm management, and we try to predict with rather good results the frequency of chattering alarms. So in this case, is a support to the to the operator that has to deal with alarms, and of course has to understand whether giving priority to an alarm or the other. And the case of chattering alarm provides information on this, let's say, priority ranking. A chattering alarm would probably need less priority than other alarms. And now let's see an example of hydrogen technologies, and in particular, let's say, relatively recent publication this year on the use of machine learning in order to support risk-based inspection planning. So now the idea is that risk-based inspection planning is supported by standards that are rather popular and consolidated, such as API 581 is one for all, is very much used in the oil and gas sector, but it is not very good for hydrogen technologies. It doesn't take into account some damage mechanisms, damage factors that may occur from the interaction between hydrogen and metals, okay? And in particular here, we wanted to model this damage factor based on the information that we collected from previous experimental tests. So we fed this database obtained from experimental test to a machine learning algorithm to produce a model that is able to produce such damage factor based on the operational conditions, okay? So we would be able to obtain a damage factor that is describing the influence of hydrogen on the fatigue crack growth in hydrogen pipelines. These would be one of the let's say elements that will allow us to define a value of associated risk that varies with time for the equipment for the pipeline, and will allow us to understand when this value of risk will reach the threshold that says, look, an inspection is required. So this is the overall idea, but I must say that there is quite a larger research behind such summarized description of the work. Another example was given by this work of last year that predicted hydrogen concentrations in the case of liquid hydrogen releases or the formation of liquid and solid oxygen, because condensed phase explosions, so detonations in case in which there is liquid hydrogen, liquid oxygen, or solid oxygen, we might want to avoid them. And a prediction ahead of time would be definitely useful if we want to prevent or avoid them. Last example, I must say, is not 100% what the title says, in the sense that I showed this example as a potential for learning from past accidents. What does it mean? It means that in the reference here at the bottom of the slide, I send the audience to a paper that is reviewing scientific literature. Okay. While the idea would probably be reviewing past accident databases, not scientific literature. But at the moment, the quality of past accident databases leads to some difficulties at obtaining, let's say, meaningful results from these approaches. These approaches are unsupervised clustering activities, unsupervised machine learning that allow us to, let's say, group the items, the records by topic, by thematic, okay, and allow us to understand what is, let's say, the connection in such clusters in order to have a better understanding of what happened in the past and what we can do for the future, okay? And yeah, here is a brief overview of how these algorithm work. I showed the case studies, and sometimes I've anticipated these methods. But on the overall, the first 5 examples, the first five case studies, all used the supervised learning, where there was an algorithm that trained a model based on a portion of a database, and then tested the model based on the remaining portion, okay? While the unsupervised learning is meant to recognize, let's say, a pattern in the records of a database, so to recognize similarities and differences, and based on these similarities and differences, to group them. However, such grouping at the end might be meaningful or relatively less meaningful. So I must say that with the results we obtained, we could identify some patterns that were not as obvious, but definitely were there. And sometimes we actually could understand that a pattern was probably missing in some of the clusters. However, it's an interesting way of regrouping your database items and learning more from them in an unbiased way, because it's unsupervised. When we test these results, we used some metrics, and one of the most popular one is the accuracy, okay? And it's generally let's say, the reliability of the model obtained from the algorithm. We might have precision, that is basically the ability to avoid false positives, okay? To be precise, you know. And recall, which is instead the ability to identify all the relevant instances, okay? While the curve under precision and recall, the area under the curve of precision and recall, it's a trade-off between the two, and gives us information, let's say, on whether we can possibly optimize our model as well. Why do I say this? Because sometimes there is the need to optimize such models. And in particular, we probably have read also on the news the problem of alignment in such artificial intelligence models. Well, maybe you didn't read it as alignment. Maybe you read it as, I don't know, ChatGPT is providing results that are only fitting for the Western world, for the white male. The idea is that results are biased based on the input given. And ChatGPT, for example, the input given is internet, okay? While on the other hand, we might want to align the model on some values, human values, okay? So we would like to overcome such bias. And in particular, for safety, we want to align these models on the preservation of life, on minimizing environmental damage, and probably minimizing the operational losses. But I must say, with this order, life first, okay? And sometimes the models that we get probably don't necessarily follow this order. It's somehow the problem that James Reason in '97 showed with these graphs on the right, plotting, sorry, sorry about that, protection against production, showing that if we push too much and invest too much on protection, we might end up in bankruptcy. But if we instead push too much, invest too much in production, we might end up in major accidents, okay? So there we might need an optimal alignment with these priorities. What do we do then? We shouldn't look only at one arithmetic. Accuracy for sure is not the best one, especially if we're talking about process safety, where major accidents are rare events, fortunately. So a model, an artificial intelligence model, would tend to say that they never happen. Okay, in this case, the accuracy would be high because let's say 99% of the time it would be the model would be correct. But the 1% of the time that we care about it would be a big problem because the model says nothing is going to happen, but then we will have a major event. So what should we do instead? Look at the recall metric that is focusing more on true positives in the sense that I really want to identify all the events, okay? Even if sometimes I have some false negatives, okay? Even if, sometimes I might, let's say that something happens, but it doesn't, okay? If I said it correctly, I hope you understood. In the case in which I have events that I have a relatively lower consequence but higher frequency, we might even want to look at the metric of precision, in which I would rather be more precise and it wouldn't be such a big problem if I miss the identification of one, let's say, small mishap or near miss. How can I do that? Well, there are approaches for optimizing based on these metrics. Here is one of them. Sorry about that. Un secondo. And this can be done through different approaches, algorithms. And meta-learning is one of them that allows you to optimize the parameters also for these machine learning algorithms that are meant to produce models for these applications. Thank you.
Thank you, Nicola, for your extensive presentation and for warning us also for the possible drawbacks of utilizing machine learning and artificial intelligence tools that are widely available also for non-expert and which can drive non-correct conclusions. Now we have room for one quick question, if any. No question for the public. So you were very clear and you provide also some information for non-technical and for non-expert in AI, I believe. Thank you once again, and I wish you all the best. So we can move towards the conclusion of this event, and I can see that, and I'm happy that we have large attendance till the end of the webinar, and I wish to thank the keynote speaker for sure, all providing us food for thoughts, and all the virtual delegates, especially those stimulating interesting discussion, and students who represent the next gen. We hope to have other events like this in light of the ongoing energy transition and the required risk consideration and assessment method changes in the days to come. If possible, I'd like just to close this 7 spotlight talk by the Loss Prevention Working Party by recalling the next event, the Loss Prevention Symposium. I kindly ask to Martin to display the presentation, the last slide. if not possible, we can go down to the last. Yes, sorry. Yes, this one, because you know that I mentioned that the next loss prevention symposium will be in Bologna, and you know that there is a consideration for young people, and as usual at this symposium we shall have the EFCE Excellence Award in Process Safety, which is aimed to PhD thesis published in the preceding 3-year period, which demonstrates an outstanding contribution to research and/or practice in the field. You can find all relevant information on the EFCE website, and I show you that the closing date for nomination is 31st of December 2024. So please apply if you have a clever and outstanding PhD student. And at last, I recall that the call for paper for the symposium is still open, but there is a very narrow time span, as it will close definitely by 20th of November. And so I can conclude, and here you can find all the mails for any comment or any question for the speakers. And I'm personally very proud of this webinar. I thank you all for listening, and please enjoy next spotlight talks in the coming days. That thanks to EFCE allow promoting the advancement and the cross-disciplinary scientific exchange of knowledge of safety and loss prevention. Goodbye to all.
Thank you very much, Bruno. Also from the board of the EFCE, thank you all for watching, and have a nice weekend.
Goodbye. Thank you.
Bye-bye.